and it's a great pleasure to be here. And to be honest, the second project I'm going to be telling today about is even partially, exists because of visits here, because there I met my collaborators and started working on it. And today I would like to tell you actually not one story, but two related stories, and they're kind of related to each other. And I think talk should be very simple, right? If you know Pauli metrics and know how to make your coffee, you should follow. And if you're not following because language is different between different communities or something else, interrupt me, right? So maybe let's leave the conceptual discussion if this physics is all wrong or something like that towards the end. But if you're not following, please stop and ask. So yeah, I will start by acknowledging the team, local team at IST Austria, where I work, and the team of collaborators on the second project, and also many, many other people with whom I had the pleasure to work on scars and quantum models, and also a couple of funding sources. And let me go to show the same picture you saw already 3 times, I think, during this conference. Maybe it's going to appear more, right? I think previous speaker maybe showed part of it. I'm going to show the whole. Beautiful experiments checking about how heat bath emerges in isolated quantum system. And that probably doesn't need much introduction. You have an isolated quantum system, you do a unitary dynamics, system stays in a pure state. Yet at the same time, subregions of your system start looking like they would be coupled to a heat bath and they reach some effective thermal equilibrium. And again, I'm omitting details of how this was implemented, and I'm just asking the question, is thermalization inevitable? And before that, right, I would want to also connect this thermalization dynamically. When we start with our system, we observe a small part of it and see that this part reaches thermal equilibrium, to properties which theorists like a lot more, eigenstates, right? Eigenstates is an infinite time property. For that reason, they're nice. And also in eigenbases, quantum dynamics becomes ridiculously simple, right? You took your initial state, expanded it over eigenbases, now acquired a bunch of phases, and that's it, right? There is nothing else is happening. So eigenstates stay eigenstates. The only thing that occurs is dephasing between them. So then, intuitively, we can arrive to thermal equilibrium if we say that all of these eigenstates are thermal, and then maybe add some extra assumptions on absence of resonances or that these phases randomize sufficiently well. And this goes under the name of eigenstate thermalization hypothesis. And loosely speaking, right, we would say that eigenstates are random vectors up to symmetry, conservation laws, and this gives a lot of interesting predictions. For example, we would expect that highly excited eigenstates would have volume law entanglement, as I'm showing, for example, here in numerical illustration from this review by Anatoly Polkovnikov and others. We would also, right, believe in this eigenstate thermalization hypothesis ansatz that's saying, for example, if we measure local observable in eigenstates, it must be smooth function of energy. And that would guarantee us that our normal physical system equilibrates. This local observable would equilibrate to something that is also ideally agrees with our thermodynamic ensemble, microcanonical or macrocanonical. All right, so far so good. And from here, maybe we're getting idea that non-ETH eigenstates or some systems where some of these pictures goes wrong are also interesting dynamically, right? That if we have that system in your quantum simulator, you're also going to observe potentially interesting dynamics. And that's indeed true, right? We know one example where thermalization goes wrong, so-called many-body localization, and the idea would be that system there is governed by emergence of quasi-local conserved quantities, and quenches behave very differently. So you do quench in your favorite chaotic model, Ising model, or some other models that you got in your quantum simulator. Entanglement will be spreading ballistically, everything equilibrates. You take disorder, do many-body localized system quench, and you see entanglement spreads logarithmically, ridiculously slowly. System will keep some memory of initial state, and it's different class of dynamics. Now, I think it's interesting, right, to ask what's in between. And you know that you already saw some pictures showing so-called quantum scars, and I'm going to explain what it is. They're kind of in between, but I want to be greedy today. I want to be not just in between, but I want to be exponentially probable, right? So exponentially many non-thermal eigenstates probably still measure 0. So they may be still invisible for all other characteristics, but let's be more greedy. Let's ask not for polynomial states, not for one special states or L states, but for exponential number of states that are strange. And then the idea would be either we can ask for states or for quench configurations, right? So we can ask for eigenstates. Again, this would be infinite time properties of our system, or for initial configurations, and then quenches from these states would lead us to interesting dynamics. Okay, so far so good. So that's my kind of objective. And today I'll speak about two different topics, which again are related by this common idea. And first one would be actually Rydberg atomic array, and just to show you some other examples of interesting quenches to do there, especially since there are so many experiments being presented here. And also after that, I'll switch gears and go into this quantum systems with thermal phase transitions. So to introduce atom arrays, probably I don't have to show this slide, but let me quickly go over it, right? So we trap Rydberg atoms. Hamiltonian is Ising model written in an interesting basis, right? Instead of sigma z operators, I'm using n, which are projectors onto upspin in my language. And in a particular regime, this model can be simplified, which I'm going to tell you in the next slide. And this is one of these observations of quantum scars or atypicality in this model that was done together with Harvard team, where you prepare some initial state, in particular this neo initial state on any bipartite lattice. You can prepare it on honeycomb lattice. You can prepare it on one-dimensional chain. You measure density of Rydberg atoms on sites A and B and see that it reveals relatively long-lived oscillations. And the surprise is that you have another state with the same properties from thermodynamic perspective. It's also zero energy density state. This is highly excited state, as highly excited as this one. And in this state, you see that local observables behave like they're equilibrating. Of course, from a previous talk from today, we now know that this name observable equilibrates, but this state also has some funky business going in it. But I'm gonna defer interesting people to this paper that recently appeared on the archive. So this model displays some atypicality. And this atypicality can be distilled and understood a bit easier if you go to the effective Hamiltonian so-called PXP model. So you do Schrieffer-Wolff transformation, assuming large energy scale, namely repulsion or large interaction between two excited Rydberg atoms nearby. And then you're allowed to discard other terms and have this very, very simple Pauli matrix type Hamiltonian. Again, each spin is being flipped or doing Rabi oscillations, conditional on both neighbors being in a ground state. Right? So you cannot have Rabi oscillations if one of your neighbors is excited. That's it. And now simulating the experimental setup, you can start with Z2 initial quench, and you not only see oscillations of local observables, you see a revival fidelity of a full many-body quantum state. Right? You see that your Z2 state, you start with it, and this is the blue line, and it approximately returns to itself with a relatively big probability. And then it decays. The same happens for Z3 state, and then for Z4 state, and this is this atypicality. Suddenly you don't see any revivals, right? You see that with Z4 state, probability shoots down, and then there is like some tiny fluctuations down there. So that would be the expected behavior. Okay, this model has atypicality. And in 2018, right, we understood and attributed it to this polynomial number of special strange eigenstates in the spectrum, and I call now at least because it has been several years passed since this time, so now we know that there is a lot more strange things happening about PXP, and that's the only thing that I would like to show in this first part of my talk. So these special eigenstates, we understood them from some algebraic construction and other approaches, and you see that they're maximally far away from your canonical ensemble prediction. Right, so you see that these eigenstates don't like to follow to what your canonical ensemble tells you expectation value of local magnetization must be, and there again, as far as it gets. But of course, it's obvious that other states are also doing something weird, right? There are many, many other states here. This is density of dots, and you see most of the states here, but counting how many are outside is hard task, and understanding how many eigenstates are also non-thermal in this model is also hard task. Some call came a few years later where together with Latko Papic, we studied transport in the PXP model. It has only one conserved quantity, energy density. And turns out that energy density at infinite temperature, so at typical initial states, flies away faster than diffusively. And that is surprising, right? Because it's a model which has level repulsion. We would expect that it is chaotic, and generally would expect diffusive energy transport. And this brought us to the question, can we find energy carrying excitations in the PXP model? So who carries this energy, right? If there is some strange business happening there that energy flies not ballistically, but maybe faster than diffusively, what's up? Yes, so I see some people raising hands. Somewhere in between. So non-ballistic, the exponent coincides with KPZ. We have no idea if it's KPZ or not, but the exponent agrees with KPZ. Okay, yeah. So can we find this energy carrying excitations? And here credit goes to my group, and the answer is yes. And this is an example of quench. So this is PXP model, unitary dynamics. It's done on a big system, 150 sites, numerically, just to see no boundary effects. What is done is system initialized in a uniform initial state that is reviving. So system is doing scar oscillations. And that's what you see here, right? You see this kind of pattern. Scar has no energy density. So if you plot expectation of energy density, you see nothing. You see white background. Now, students and postdocs identified class of defects that are only 3 sides. So this is a factorizable initial state. It has 3 sides, 3 sides, 3 sides, 3 sides. And now these 3 sides are in a special state. And these 3 sides are also in a special state. And these as well. And you see that typically what you would expect is that defect would cause some Lieb-Robinson spreading of perturbation. And here, instead of Lieb-Robinson, it just coherently moves one direction or another. Moreover, these defects can be endowed with energy density, right? You see that there is a blue color defect and a red color defect, right? So there is really localized defect that manage to carry energy ballistically. They don't have dispersion here, right? Because they must be enslaved to the scar period. They are living on top of oscillating vacuum. If this vacuum oscillates at one frequency and soliton moves with another frequency, it's going to start decohering vacuum and die away. Right? So they're a bit strange objects. They exist, if you wish, in a Fouquet background. Okay, what are these? Right? And I don't have a complete theory, so it's not going to be satisfactory if you expect me to, I'm going to explain you where they're coming from and so on, but let me sketch 2-3 elements of construction. So, turns out that these energy solitons have their relatives, neutral solitons, and they're a bit less spectacular. So you see here simulation with a neutral soliton, and there is a line to emphasize that there is something happening there. But intuition is very simple. So this scar vacuum is a coherent oscillation of some pattern, and this pattern stays factorizable at certain periods. At certain periods, state is factorizable. Now, we can introduce fast-forwarded defect. So we take defect from, we take a unit cell which is shifted from T/4 and insert it back into our state at T, at 0. And now this defect miraculously starts moving right. Now, not surprisingly, if you would introduce defect backward in time, right, at period 3T/4 or minus T/4, this would be flying left. This is a phenomenological observation. All of them are relatively simple, right? You see that this initial state is some weakly entangled superposition. This defect is weakly entangled superposition. So as soon as you have quantum simulator capable of producing short-range entangled states, this can be simulated. And now this is the light cone of this neutral soliton. So this is a difference between scar oscillations, right? So I subtracted this kind of homogeneous background. And now it's more clearly visible that Lieb-Robinson thing is very, very asymmetric, right? There is almost nothing going to the left. There is some disturbance, but most of the thing is flying in one direction. Now, energy solitons are not very hard. Now you take a coherent superposition of these objects with your vacuum, with the correct phase, and voila, they have energy density. And now, as I said, they carry, they collide, energy on total is conserved. So for example, in this quench, you see that positive and negative energy soliton collide. I measure energy. At some point, I get energy spikes. Here you see that energy is approximately nearly 0 at the point of collision. And then they are not perfect solitons, so properly would be called them quasi-solitons. They don't survive collisions ideally. Part of the energy gets lost in the collision, and generally things are decohering. Okay, so far so good. So just coming to the conclusion of first part, we found an exponentially large subspace of initial quench states. And why exponentially large? If you like, you can now alternate scar or soliton. If you don't want them to collide, put only left movers or right movers, right? Then they'll never be colliding. They're just going to be flying all together in one direction. So there is a lower bounded by something like 2 to the power L over 3. You can bound, depends on your preferences, but there is an exponentially large space of initial quenches where these solitons live, and it's hosted on a short-range entangled initial states, right, which is important. So you can, again, launch the subspace by short-range entangled initial states. A lot more questions remain than answers, right? I don't have any theory. We have only phenomenological results about lifetime, stabilizations, experiments, and study of inhomogeneous quenches. And on this front, right, let me advertise this bell pair quench. So if you want, you can launch a bell pair of solitons in the energy space. So this is left and right mover, positive energy with positive energy, negative energy with negative energy. And you see they fly away, they launch this extra entanglement in your region, and you see that there is a connected correlation function on the light cone, as you expect. Right? So maybe they can be used to create some sort of EPR pairs in your Rydberg array simulators, if you care. Yes? Very good question. Yeah, so I think PXP model would have, at a Trotter step pi half, it would have solitons as well, so that it's integrable. And it's a big question, is they related to this or no? Because here you see everything is entangled, and that's a bit of a problem of relating them to each other. It's not so easy. Okay, so that's the first part of my talk, right? It's more maybe questions and answers. And unless there are other quick questions, let me proceed to the other part of my talk. And now I actually want to think about thermal phase transitions. And if I start with quantum phase transitions, we have second order, quantum phase transitions, our favorite, universal, everything, and an orphan child, right? And now we go to a thermal ones, and it's the same, right? If you think about thermal, many of us probably have written Monte Carlo codes about, classical second order phase transitions, and we know that there is universality, exponents, and so on. And, everybody makes coffee, right? And you boil your water, and that's this. That's a first order phase transition. Okay, maybe not quantum, but it's a thermal first order phase transition, and yet, we usually don't like it. It's non-universal. So today I want to think about ETH in this regime and properties of eigenstates. And I think it's interesting for the ETH and properties of eigenstates just because it's more singular. So second order was studied by David Hughes and Srednitsky in some other contexts. Again, they studied finite temperature second order phase transition in quantum systems. And my point is that this is a bit easier to see and a bit richer just because it's singular and also it's more generic. So just a review, right? You have your coffee, you use temperature, you cross some phase transition line, and you expect some discontinuous change in properties. This is not relevant, or not so relevant, just because I like microcanonical ensemble. So I shift my gear, I switch off temperature, I have Hamiltonian of an isolated system, and I tune energy. Now, in a textbook, first order phase transition is something really, really strange. Nothing bizarre happens, it's just your density of states is non-convex. Right? You have this intruder in the density of states. And if you take derivative, you see the temperature does something very strange, right? You increase energy, temperature keeps rising, and then it starts lowering. And you say, what the heck, right? Temperature cannot lower when I raise my energy. And indeed, systems with locality, they don't like this region, right? That's going to be the region where metastable or completely unstable microstates live. And what you do in a physical model, you organize so-called Maxwell's contraction. And that's exactly boiling of your coffee, right? You have some part which is water, some part which is vapor, and you have domain wall between them, and there is some flow of one state into another. Okay, so I will sacrifice locality just to do some analytic progress. And today I will think about this picture, and I'll make it specific, but you see hopefully the analogy. I'll take density of states, which has two branches, and they cross. And you see it's much more singular than here. Right here, everything is smooth and nice. Here you see really temperature is going to be jumpy and so on. So let me kind of illustrate it. So now my talk goes into two branches. There's going to be conceptual branch, sort of, for those who like conceptual pictures, picture is this. Now if you think what the heck it is, right, where's my model, where's my Hamiltonian, there is a second slide which explains the Hamiltonian, right? If you don't like Hamiltonians, stick, we're going to return back to conceptual slide. So Hamiltonian is LMG 3-spin model. It's an Ising model, but with 3-spin interacting, all to all. It's a mean field model, so we're going to solve it almost to death. And how we're going to solve it? We're going to solve it with a density matrix mean field. So we're going to take, for this model, product state density matrix ansatz. And we're going to have spins which point somewhere, and there's going to be a spin size. And how I use the spin size? The spin size is the idea that you have auto model, it has permutation symmetry. I can add all spins, and I can add all spins into maximal spin sector or smallest spin sector. And that's the spin size which controls how I add them. And if I have a maximal spin sector, there is zero entropy. There is a unique way of combining all spins together into one giant one. If there is zero spin sector, there are many. So my entropy is inversely kind of my spin size. The smaller spin size, the larger entropy I'm dealing. Now, mean field is ridiculously simple. Mean field tells me maximize entropy or minimize n. And you see immediately how this model gives me first order phase transition. I have constant energy contours here as a function of spin size and my angle. And you see that at small energy densities, I have a unique minimum, this blue arrow. And then suddenly another minimum pops up. That's a classical first order thing, right? There is one minimum here, there's another minimum there. They don't care about each other, no Z2 symmetry. They just like that. Now I plot value of spin at minimum, and I convert it to the entropy, and I have these two branches that I advertised to you. Right, so there is one minimum where ground state starts from. First entropy is 0, and then entropy grows, it goes down. And then suddenly this guy will appear, and you see it will overtake it in entropy. So eventually, this state is much better than this one. First, they other order, and they actually don't care about each other. You see that they have different value of angle, so expectation value of magnetization is as different as it gets, and doesn't care about each other, right? Again, no Z2 symmetry, two generic branches. So far so good, yes?
Why do you call n as an entanglement?
Yeah, so the question is why do I call n as an entanglement? Intuitively there is an equation for that, but the idea, as I explained this, I come from a bunch of spin halves, and I add them together. If they are maximal spin, n is going to be equal 1 here. So that's zero entanglement, right? That's, once you start here, there is entanglement is 0, you see? And then once n is 0, that's maximal entanglement log 2 per spin.
So those Z and X are not Pauli Z and X, is not a logical Z and X of the multiple?
No, this is actually Pauli Z and X of a multiple spin, and the density matrix is a tensor product of all of them. But the idea would be that this n then would still be describing entanglement at a semi-classical level. So again, maybe we can discuss this later after the talk. Great, so hopefully I illustrated this kind of impressionistic picture by a specific model, right? So there is a specific model where there are two branches, two phases, and they swap in the density of states, right? There is one phase which is, your water, another phase which is your gas, and suddenly there is a point when one overtakes another in density of states. I don't allow phase separation because it's all to all. Now question, what do I do with my ETH, right? I have two expectation values of my local observable in this picture, for example, specifically, right? Z can be positive or negative at the same energy density with different number of eigenstates, right? So now we can have what I call multi-branch ETH, where O is going to be smooth, multi-valued function of local energy density. Or I can have, I would call it mixed branch ETH, where actually this branch you see here, far away, red branch is exponentially subdominant. It has much less density of states because this is, a density of states is exponent of my entropy. So I can have this ETH, right? So which one wins? And actually answer is complicated. Answer turns out that both can be there. And for that, I can do another calculation in our model, and I'm going to omit details, but since it's a semi-classical model, we can again solve it almost completely. So we'll be doing calculation of quantum tunneling between two branches. So how can we quantum process flip magnetization between here and here? And turns out that your matrix element is going to be exponentially small in a system size, not surprisingly. But the key is that now level spacing is also exponentially small in a system size, or each branch has finite entropy density. That's my level spacing. So now I have a fight between two exponents. And now it's a bit like many-body localization transition. If matrix element loses, I keep my branches. If matrix element wins, I will start hybridizing my eigenstates and quantum tunnel from one branch to another. And now I can make it again really quantitative. So this is mean field phase diagram of this model. I'm changing these two couplings, and I'm plotting where this crossing is happening. So sometimes this crossing is not happening, sometimes this crossing is happening at a certain energy density. And I'm also checking, is there this phase transition here in my mean field? And you see that there is a line separating multi-branch and mixed branch regimes. Okay, so with mean field, I feel very powerful. I say that, look, maybe if I go with my exact thermalization around here, I have a chance of observing it. Why? Because you need to have very, very high density of states there, because you want to have many eigenstates in your matrix. You're going to diagonalize a full matrix, so you need a lot of eigenstates. And I also want to cross this guy here. Okay, so let's realize the strange ETH, right? So still another kind of abstract slide. We have this scenario. And what will be happening is that at some point, there will be multi-branch ETH, and then at some point, quantum tunneling will come in, and one of the branches will get eaten. And now, it's your call, which one is more interesting. In this regime, there is non-complete ergodicity, right? You really have one branch and another branch. And in this regime, there is ergodicity, but there are cat-like eigenstates, right? Eigenstates here, because they quantum tunnel between two branches, are going to have really bimodal distribution of local observables. So going to be really strangely fluctuating magnetization in them. So let's observe this in ED. So I take this model that I advertised, and the only thing I have to do to it, I have to break permutation symmetry by terms which are thermodynamically irrelevant. So I add small terms which couple all spins, break this stupid permutation symmetry I had to add to solve it via mean field, but are invisible. And now you see this is ED numerics for this model. So you see what I promised to you, that there is one branch. This is superimposed with mean field solutions. There is one branch and another branch. I'm zooming into this tiny region, right? You see that energy density around 0.2 is a very interesting thing that happen. So this plot is zoom in of, these curves are the same curves as these. And you see that indeed at some regime I have eigenstates following one branch and following another branch, but then these poor guys with negative magnetization disappear. Ask, where do they go? Actually, they melt into the higher branch. Because if you plot distribution of eigenstates, you take eigenstates here, plot distribution of magnetization, you see this bimodal distributions that I promised to you, right? So it's really the scenario that I'm melting one branch into another. And then since I am kind of like God here, right, I know everything with my ID, I can fix it. I can really cut my bimodal distribution in this peak, and for each dot I will put, for each eigenstate I'll put 2 dots, depending on which branch they are. And you see I fixed my mean field. Right here, mean field didn't work so well, and now I took and fixed it. Again, this is all unphysical. This part is unphysical, because here I'm doing something strange with my ED knowledge of eigenstates. Right? But you see that indeed these regimes are realized, and again, I would call it multi-branch and mixed branch regime. We can move it depending on the quantum field. We can make this kind of hybridization happen before crossing or around crossing. And let me just conclude with discussing dynamical signatures, because I also had some questions, so maybe you allow me 5 more minutes. Dynamical signatures of this, I think should be there and should be feasible, because now these 2 branches, they're actually physical states. There are exponentially many states in each of the branch. So with your quantum simulator, you should be able to prepare physical states that has maybe negative or positive magnetization. And then the idea would be that before branches mix, there is a full stability, right? So you can prepare initial state which has positive magnetization. Magnetization is not a symmetry in your model, yet it's not going to be melting, right? It's just going to be living on this branch, and that's it. It's going to dephase, relax, but magnetization is going to stay. Now, in a mixed branch regime, the idea would be that you can go here and prepare a state with a negative magnetization. And it's going to be a very strange state. It's going to be superposition of these guys, but such that positive magnetization components cancel out. And you're going to do time evolution, and your magnetization will be relaxing. But it's also going to be exponentially slow process, at least here, because we have matrix element always comparing to the level spacing. So, there are dynamical signatures of this, and of course, model is non-local and all-to-all, but the idea would be that moving to the more physical models, we can find more signatures. For enthusiasts, there is also spectral function behavior here that also behaves anomalously, and I think that's a consequence of this dynamical phase transition. So now, again, let me show you for the 3rd time the same conceptual picture. This is what we studied. This is what is realized, right? That ATH sometimes can be multi-valued. Sometimes one of the branches disappear by quantum tunneling to another. And in this regime, I find it's even weirder because there is bimodal distributions. Now, if you believe in the rules of the game like your Lego, you can play into interesting games. Let's say these papers by Srednitsky and David Hughes was term of 2nd order phase transition. So there, these branches just coincide. There are two branches because they're related by Z2 symmetry. Then there is a false vacuum decay, where you take your Ising model and just add HZ field. That just shifts one branch with respect to another. There is no crossing, right? One branch just got suddenly suppressed in energy. Maybe if you write 5-spin interacting model, you're going to get this mean field, right? And then maybe something interesting will be happening there. You can couple positive infinite temperature states to negative temperature states and so on. But most interesting, of course, to realize this in long-range systems or even local models. If you have two-dimensional Ising model, that may be already enough. And also understand if this can give rise to exponential families of scars, right? Because in some setting like this branch is always subleading. If it gets eaten up or not eaten up, that maybe can be interpreted as scars. And with this, let me just conclude. So I showed you some exponential soliton subspace in PXP model, where these solitons are just weakly entangled three-side defects that coherently spread your energy. And I also discussed potential generalizations of ETH in a system with a first-order term of phase transition. And this has been already thought about in the context of Z2 symmetry breaking. Without Z2 symmetry breaking, picture seems to be richer. This is your toy model, if you like. And I think there are many, many open questions. And with this, I'm happy to stop.
Questions? Yeah. Could you go to the speaker?
Hi, Maksym. Great. So, what did you do to agree the ED with the mean field solutions?
Yes. So here, I was a bit quick here. So if eigenstate is bimodal, for each eigenstate, I plot distribution of magnetization in the eigenstate, right? If it's non-bimodal, I just put a dot. The dot is going to be gray, and you see the gray dots are either one or another. If the distribution is bimodal, it has these two peaks. I cut it in the middle at the minimum, assign one peak to one branch, renormalize it and put a dot here, and assign another peak to another branch and renormalize it and put a dot there.
I see. Those are not eigenstates. No,
those are non-eigenstates. Those are like fixed eigenstates or uncoupled eigenstates. Uncoupled eigenstates. That's why I said that this is unphysical and you need to do ED to do this ETH fixing.
I have another question. So, in the thermodynamic limit, shouldn't this mixing phase should go away because eigenstates are like locally distinguishable, but at every site. So any local matrix element shouldn't be able to connect them.
Yes, I think the answer is that level spacing is exponentially small, and matrix element is also exponentially small. So it's exponent against an exponent. And in that sense, I think this is a transition. So there is really, we have a semi-classical calculation where you really calculate this prefactor and this prefactor. And if one beats another, so there are exponentially many states. And to connect them, you can't have to flip all spins. That encodes exponential cost as well. But one exponent can be larger than another or smaller. And then it's going to flow one way, it's going to couple better and better, or flow another way. So it's a bit like MBL transition, level spacing matrix element. Who wins? Hybridization wins, is going to win better and better for bigger systems. Hybridization loses, is going to be more and more localized for bigger systems.
Let's chat more.
Let's chat. Sure.
Hi, thanks for the talk. Could you explain the intuition to choose this microscopic model? So why the three-body interaction?
Yes, that's a good question. Just because Ising model, which is very well studied and well loved, it has a phase transition, first order phase transition that is tunable only by field. Because of Z2 symmetry, right? The phase diagram looks like on the temperature axis, we have a temperature Hz. This is a line of first order that terminates in the second order. Right? So you cannot cross it by temperature. Right? And then you need some of these terms to move it to break the Z2 symmetry, but then you can throw away Ising term. So we can add Ising term here, it's going to be as good, but I think this one has to be there to break Z2 symmetry beyond single particle level.
So here there's no symmetry, right, in this model?
This model has a chiral property. This has another symmetry. There is a chiral operator which changes energy into minus energy. That's why everything is symmetric in this model. But it's not important in a sense that I don't think it influences physics. I just don't have to study other side of the spectrum because of the symmetry. I know it's exactly identical.
So if I can ask the second question, if I wanted then to, say, go from your conceptual picture to a model building, what should I look for if I want to see this kind of branching ETH? What is the hint that I might see this?
Well, my understanding would be that you need, in this mean field model building, you would take probably higher spin interacting models. So 3-spin interaction works. If you add Ising term, probably you'll be realizing already something more complicated. So the idea is to just go beyond Ising because it has Z2 symmetry, and if you break the Z2 symmetry only by adding magnetic field, it's not good because of this phase diagram. So anything beyond, I think, is good, but the irony is that we rarely study models beyond, right? That we like our Ising just because it's so nice and it's also so realizable and so on. But.
Thank you.
Yeah, I have a question about the matrix element.
Mm-hmm.
So the intuition for why this can be so small, does it have to do with the fact that this is an all-to-all model, and how would you expect this to change?
That's a great question because we lose. I think that's exactly two interesting questions, right? Either long-range systems or really fully local models, and then all this analytic control and all this calculation goes into the window. So again, here it's just exponentially small because of semi-classical approximation. We really take this energy landscape. We really take this kind of energy landscape and really calculate tunneling from one minimum to another. And then you go under the barrier, and it's a semi-classical system, so there is an n prefactor. So this is, this is a result of this analytical calculation. There is some terrible integral, right, that gives you this prefactor, and this prefactor you know from the exponent, so you really compare them and get this analytic phase diagram. In power law models, right, the idea would be that maybe power law models with not very fast decaying power law are still a bit within this mean field realm, right, that you can use them as a all-to-all plus perturbation, and perturbation is needed to break this permutation symmetry and make model obey candidate for checking ETH. So, and I have some support for this hypothesis. For fully local models, to be honest, I don't know, because there this physics becomes very rich. There is this phase separation physics, so you can get domains of one phase inside another phase. But my speculation would be that it's still interesting signatures because of that. But they may have to do with translational symmetry breaking or some interesting translational symmetry. Maybe your eigenstates are going to be cats in translational kind of sense, that they're going to have this, your bubble of vapor is going to tunnel in your coffee mug and be spread out through your coffee mug, something like that.
Yeah. Okay, I did have a question about the local and phase separation, but maybe I'll ask a different question. So in the LMG model, there's some kind of like super spin representation of the mean field dynamics, right?
Yes.
Just on the block sphere?
Yes.
Is there a way to visualize all of these like thermal phase transitions on these kind of pictures?
I would say not naively, because you see, I want entropy here. So usually what you say, I have an LMG model, I will solve it in a bigger spin sector. And that's solvable because, you can solve it for 1,000 spins, because your spin, you're going to have 1,000 by 1,000 or 500, like 2,000 by 2,000 matrix only. But I'm not happy with that, right? Because maximal spin is going to be one dot here. It's the lowest entropy point. And I need to solve your LMG model in every sector and then combine them all together. And the idea would be that this perturbation that I added then would break off that symmetry, right, and hybridize them all to all, and then I have a chance for ETH. So maybe there can be still some signatures in dynamics and some signatures from this big spin sector, but it's definitely becoming less and less relevant as I move where interesting physics is happening. Because here I'm not in a maximal spin sector and I must be dealing with a huge degeneracy. I mean, this degeneracy is my bread and butter, right? I want exponentially many states. I need it.
Thanks.
Yeah, so maybe you mentioned this and I just missed it. Like, is there like any analytical understanding about the quasi-soliton? Like, you have those pictures of like different states kind of flipping between, like, so maybe one concrete way to phrase the question is like, yeah, like does this explain that there's a soliton that follows the Lieb-Robinson electron? Or?
Yeah, that was very nice. I mean, we tried to solve this from many different angles, and in the end, our paper is several phenological approaches to it. Yeah, the solidum looks a bit like a phase kink, right? Roughly speaking, you have a clocks which tick in phase, and if I wind clock forward by quarter an hour, by quarter a day, right, it somehow starts traveling, right? But you see, even here, when it travels, there is this kind of six spin entangled state, and we couldn't crack it, right? So for whatever reason, it entangles and then magically disentangles and gives you back your unit cell. And so, I mean, again, it's a bit of a nasty problem because of this oscillating background. You're dealing with Floquet system, and on top of it, you have a propagating defect. So probably it can be solved, but so far in the first work, we failed to solve it. Sorry.
Well, I guess the question was more naive, like, is there any hope for some kind of mean field description that would capture this? But
I mean, what Vinwei mentioned, maybe the closest point, is that there are cellular automaton point of a PXP model which is integrable, but there trotter step is equal pi half, and here trotter step is equal 0. And how to connect one to another, totally not obvious. And another problem, right, is that here state is entangled, so it's exponentially many bit strings. And of course, PXP model at trotter step pi half, it maps the string into bit string. It's an easy model. But here it's a proper quantum dynamics. But most likely there is a connection, just because they also exist in TP-XPP model. I didn't have time to show it, but there is a strange longer range blockade model where these guys also exist. And then you ask what's common, and nothing is common, right? Yeah. Here they are in this model. Maybe not as good, but I think kind of approximately still solitons.
okay, thanks.
So I guess near the first order transition point, I guess you have some branching out of ETH branches. Like, how should I call this? Like, you have such a like mixed branch state, or and is this robust under generic perturbation in a thermodynamic limit, or?
I would expect it to be robust as much as first order is, again, non-universal but generic. So I think by finite perturbations, things would be shifting here and there. But I don't think that this picture will get destroyed by a finite perturbation.
So I guess your simulation is a finite system size, but like in a infinite system size with just local interactions, would this behavior still persist in the wide enough range of energy window, or will the energy window get smaller, or?
I think it's a finite energy window. So I think it happens at a certain energy density, and at least order 1 away from this energy density, which is experimentally observable, we should be able to see the physics.
I see. Thank you.
So.
Thank the speaker again.